Hello everyone, this is the video lecture of section 6.2 volumes. So, first of all, let's review volume of rectangular box. So, width, length, height. The volume of a rectangular box is length times width times h. But then, width times length is actually the base area B, right? Base area B, B times H. What about circular cylinder? You learned that the volume is pi r squared times H. Again, that's the area of the base times H, right? In general, if you have a general cylinder, it doesn't have to be circular. And if you know the base area B and height H, your volume will be base area times H. Using this, we want to be able to find the volume of an object whose cross-sectional areas are known. Okay? What does it mean by this? Let's say you have some kind of potato-shaped object. And this is the x-axis. Somehow we have a CT scan for all x. So when you go through this, there will be, okay, let's say, this is cross-sectional area. Somehow, we can take a CT scan and find cross-sectional area for any given x. Cross-sectional area. Cross-sectional area function. Okay? If we know cross-sectional area function for all x, cutting perpendicular to the x-axis through x, right? Now, how do we find the volume? At least approximate value. We think about the cutting this on thin slices. All right? Think about thin slices. So, three. And let's say xi minus 1, xi. So think about this one slice. Think about this one slice. All right? Then you'll have, if you take, you just chop it through x equals x1, perpendicular to the x-axis, chop it, right? Bunch of the thin slices, just like you are slicing your potato. The ice piece, if you cut it, all right, and then put it like this, then you will have the top area is a of xi minus 1. Your bottom area is a of xi. And your height is delta x. Our delta x is the usual, b minus a divided by x. We're dividing the entire interval from a to b, a to b, by m. Now this xi is a plus I delta x. Okay? Then the volume of this I piece, this one is approximately when delta x is very small or n is very large, your cross-sectional area will be xi minus 1. And cross-sectional area at xi will be almost the same. These two values are almost the same. All right? And this shape is almost a thin general cylinder, right? So this will be base area of xi times height delta x. So the total volume will be approximated by adding this one, each volume. And exact volume will be obtained by taking, as usual, limit a of xi delta x. What is this? This is a Riemann sum, especially this is a right sum, right? And assuming that a of x is a continuous function, okay, the cross-section area do not suddenly change. Okay, this is smoothly changed, continuously changed. This is linear Riemann sum. The right side is one of the Riemann sums, right? And this is exactly definite integral from A to B cross-sectional area. So, bottom line is this. When you have a solid, and if you know cross-sectional area, cross-sectional perpendicular to the given x-axis, cross-sectional area function, then the volume of the object is integral of cross-sectional area function. Okay? Using this, let's prove this. Show that the volume of the sphere, volume of the sphere with radius r is 4 pi over 3 r cubed. You realize that you have never proven this before. You just were told that this is the case. Finally, you can prove this. Okay? Okay, so we want to use this approach, cross-sectional area. So I'm going to place, let's say this is xy plane. I'm going to place my sphere whose center at the origin, so that your xy plane is going through exactly center, right? So this is, okay? Half of sphere will be above this xy plane, the other half will be behind this whiteboard, which is xy plane. All right? And then I want to find cross-section area. By the way, this intersection of the sphere with this xy plane, when the center of the sphere is at the origin, then this will be a circle, a whole inside circle with radius r, right? So this boundary curve of the circle, the boundary curve is a circle, is circle equation. Center at the origin, radius r, right? So now, using this, I want to find cross-section area function. When I cut through, just like this, cut through this object perpendicular to the x-axis. All right. Okay. Obviously, when you have a sphere cutting like this, perpendicular to the x-axis, the cross-sectional shape will be also circular, right? So I'm going to call it, this is radius, let's say radius r. Okay, for that one. Now, if you cut it and open up here, this will be a circle with radius r. So, your cross-section area is pi capital R squared. Now, what is capital R squared here? When you have a point on the circle, y is actually your y coordinate of this point, isn't it? So pi y squared. But we want to write your cross-section area function as a function of x, because we are cutting through, perpendicular to the x-axis. And then this xy coordinate satisfies always this. So that means y squared equals r squared minus x squared from the circle equation. So, we got this. From minus r to r. So volume should be from minus r to r. A of x cross-section area function, which is pi times r squared minus x squared dx. Now this is an even function, because instead of x, if you put minus x, you get the same thing. It has a y symmetry. This is even function. When you integrate definitely even function over a symmetric interval, this is just integrate from 0 to r, right half only, and make it twice. Make it double. Twice that. Alright? So, what is it? 2 times. This is pi r squared minus pi x squared, right? So integral of this one, pi r squared times x from 0 to r, minus pi over 3 x cubed, 0 to r, big parenthesis, pi r squared, r minus 0, so r, times r, minus pi over 3, r cubed minus 0, so r cubed. So you take out pi, 2 pi, r cubed minus 1/3 r cubed, so which is 2 pi times 2/3 r cubed. 1 minus 1/3 is 2/3 r cubed. So, yes, as we expected, 4 pi over 3 times r cubed. So you prove the volume formula of the sphere. Okay? Next one. Next example. Let's say example 2. Find the volume of the solid obtained by rotating about the x-axis, the region between y equals x, y equals 1/2 of x, from x equals 0 to x equals 2. So, a volume of a solid, and after that, followed by the discussion about the solid. That solid is obtained by rotating what region? The region between y equals x, y equals 1/2 of x equals 0, and x equals 2, x equals 2, x equals 0 in this region. And rotate this one around the x-axis. Okay? Then what kind of shape are you going to get? Rotating around this. Then you're going to have something like this, right? So when it's like a cone, and sharper cone is bored out of the, circular cone, right? That's going to be the shape. Okay? No. All right. So you can imagine that things are rotating around this. So it's going to be outside cone, and then you take out sharper inside inner cone, take it out of the solid. That's the remaining solid. And again, same approach. In order to find the volume of the solid, we just need to find cross-sectional area function. Let's say this is x. We need to find cross-sectional area. Cut it through this. And then if you cut it and look at it, think about it. That cross-sectional shape will be, what kind of shape do you expect? I think it's this is called annulus, because the shape will be your outer circle, and then from here you have inner circle. Okay? So you have outer circle, radius capital R, inner circle, lowercase r, and your cross-sectional shape will be, if you watch from here, the cross-sectional shape will be a region between two concentric circles. That kind of region is called annulus. We call it annulus. The region between two concentric circles. So the area is obviously pi capital R squared, area of the outer circle minus area of the inner circle, or capital R squared minus lowercase r squared. Now we have to write down this one as a function of x. So let's take a look at it. When you have x, this point is coming from y equals x. So this is x, y coordinate is also x, right? So your r, capital R, is this. Same as this y coordinate. In terms of x, that will be just x, right? Now, for this one, this is x, and on this graph, y equals 1/2 of x. Then this is 1/2 of x. So your lowercase r is same as this y coordinate. In terms of x, that is 1/2 of x, x over x. Okay? So, this one is just pi times x squared minus lowercase r, x squared over 4. 1 minus 1/4, 3. Pi over 4 of x squared. Okay? So the volume is from 0 to 2. X runs from 0 to 2. A of x dx, which is 0 to 2. 3 pi over 4 x squared dx. Okay? So, that is 3 pi over 4, 1/3 of x cubed, 0 to 2. And 3 cancel. Pi over 4 times 2 cubed minus 0 times 8. Hey, it's just exactly 2 pi. Okay? Now, this approach is called Washer's method. Why Washer's? Because the original approach of this volume of the solid is by, slicing this one thin, making thin slices. And approximate those volume of each slice is as just like, A of xi times delta x. At them out, Riemann sum, take the limit, definite integral. So each piece, thin slice, what's the shape of that thin slice? If you have a thin slice, that will be just like, right? This is the shape of washer. The washer is a little thin metal plate between bolt head and a surface you are tightening your bolt through, right? So the bolt will be really fastened, are not going to be rattled and then unscrewed, right? That little thin, that's washer. That's why we call it washer method. Washer method is for finding volume of the region which obtained by rotating a certain planar region around a certain axis, like this. So that because you rotate planar region around this axis, if you cut perpendicular through that axis of rotation, the cross-section shape is a bunch of circular thing. All right? So in washer method, that's going to be your cross-section area will be always pi times outer radius square minus inner radius square. Okay? Let's do one more washer method. Okay, example 3. Suppose that region R enclosed by the curves y equals x and y equals x squared. Is rotated about the y-axis. Find the volume of the resulting solid. Okay, let's do it over here. So which region are you rotating about the y-axis? Region between y equals x squared and y equals x. Oh, definitely they intersect at 1. That region. So this is y equals x, this is y equals x squared. It's rotated around. Okay? Here. Now this time, our axis of rotation is y-axis. So, even though I didn't do, explicitly, when y-axis is drawn around this solid, you can approach exactly the same way as the other along the x-axis. C to D, let's say. For given y, somehow you know cross-sectional area. Say A of y. Then the volume will be from C to D A of y dy. Exactly the same approach, right? Because rotational axis is y, it's best to cut through the y-axis perpendicular. For given y, because you're rotating around this is some kind of base, right? Opening, and this will make a wall of the base. If you cut through the y, then the shape will be, again, endless, right? So if you draw that cross-sectional region over here, that will be like this. Okay? Again, outer radius minus inner radius. Okay? R. Cross-section area function is pi of capital R squared minus lower r squared. Now, we have to find this one as a function of y. So, for given y, what is this point? Capital R is here, right? Related to this point. Now this is x squared, right? On the graph. But we want to write everything in terms of y. So I'm going to rewrite this one as, this is x equals square root of y. Okay? In this case, x is positive. So positive square root of y. This part is negative square root of y. We don't need it. So that means I can write this coordinate as x equals square root of y for given y. I can write it that way. And your r is the distance along the x-axis. So this is x coordinate of this one, which is square root of y. All right? And lowercase r is over here. That is corresponding to this point. What is it? Well, y equals x. Or x equals y, and given y. Right? So this is y. Okay? So this will be pi times capital R, square root of y squared minus y squared. Y minus y squared. So you can get the area of the cross section at y. So volume is y runs from 0 to where? 1, because this is 0.11. Y runs from 0 to 1. Alright? 0 to 1, a of y dy, which I can take pi out, y minus y squared dy. This is 1/2 of y squared 0 to 1, 1/3 y cubed 0 to 1. So this will be pi times 1/2 minus 1/3 times 1, so 1/3. Pi over 6, because this is 1 over 6. 3 over 6 minus 2 over 6, 1 over 6. Okay? Alright, before I continue, let me check recording. Alright, this time, example 4. Suppose the region R is enclosed by the curve. Okay. This one rotate about the not y-axis, but y equals 2. Find the volume of the. So this is actually same as example 5 of your textbook. Example 5 on your textbook, page 442. So we are rotating the same region R as in example 3, but different axis of rotation. So let me do it over here. So I'm going to draw this one a bit small. So between 0 and 1. And we rotate this one around y equals 2. Then this will be like this, right? Rotate around this. Okay? So bottom is y base if you look at it from here, right? Bottom is base. Okay? So we are rotating around y equals 2, not x-axis. X-axis y equals 0, parallel to the x-axis. So we have to cut through, again, x-axis. For given x, okay, we have to find the cross-section area, which will be, again, annulus, right? So, which will be annulus again. Okay? So if you draw it here, again, this will be outer circle minus inner circle area. Okay? Again, capital R, lowercase r. Our region is between two concentric circles, the cross-sectional region. So we have to find capital R, which is this, which is same as not y coordinate. Look at this. Oh, we have to use original graph here. Sorry about that. This is R, capital R. Now, for given x, this is x squared, because that graph is y equals x squared, right? This is y equals x squared, and this is y equals x. All right? And then, for given x, the point on the axis of symmetry, this is x, y equals 2, right? That point. When you cut it through x, perpendicular to the x-axis, then your r is no longer y coordinate to this. It's a difference of y coordinate of here and here. 2 minus x squared. Okay? On the other hand, your lowercase r is, what is it? This one is along x and x, right? Because it's on the graph of y equals x. This lowercase r is the y coordinate difference between this point and this point, 2 minus x. Therefore, in this case, your cross-section area is pi capital R squared minus lower r squared. Capital R, 2 minus x squared squared, 2 minus x squared. Okay? So you might want to distribute 4 minus 4x squared plus x to the fourth minus of 4 minus 4x plus x squared. That is 4 and negative 4 cancel. Plus 4x minus 4x squared minus x squared, so minus 5x squared plus x to the fourth. Okay? Therefore, the volume is from x runs from 0 to 1. Okay? X runs from 0 to 1. A of x cross-section area function integration with respect to x, which is you can take pi out 1 4x minus 5x squared plus x to the fourth dx. I mean, this is really easy. Integral with respect to integral of polynomial. If you want, you can check the detailed calculation in the book. Okay? This is the main part, finding your cross-section area function. Okay, and you're going to get 8 pi over 15. All right. Now, this time, next one, example 5, is same as example 6 on page 444. Again, we're going to rotate the same region R as example 3 and 4, but this time rotating around like x equals -1. X equals -1. Okay? So same region, but rotating around dx equals -1. What's going to be? X equals -1. So you have this region, y equals x squared, y equals x. X equals -1. This is y-axis, which is x equals 0, right? The line equation. So your region will be something like this. Right? Again, a base, bottom is base. So this one, the rotational axis is vertical, same direction as y. So we have to cut perpendicular to the axis rotation, so perpendicular to y. So for given y, what do you get? You get this region. Again, this will be an annulus again, so we have to use washer method again, right? We just need outer radius and inner radius, right? So let's do that. This will give you outer radius, capital R. So that means difference of x coordinate of these 2 points when you go through y. And you have to write everything in terms of y, right? In this case. Then you want to write this equation as, again, x equals square root of y. And this one is x equals square root of y given y. This is, well, x equals -1 for given this y. So, this time your capital R, outer radius is this x coordinate minus this x coordinate, horizontal distance. So this one, square root of y, minus -1, which means square root of y plus 1. Right? And inner radius comes from here. Inner radius. Again, this is y equals x. You can write it y for given y. X coordinate is y for given y. Again, x coordinate difference between here and here is y minus -1, so plus 1. So for this, your cross-section area is pi capital R squared minus R squared will be square root of y plus 1 squared minus y plus 1 squared. So what do you have? Square root of y squared is y plus 2 square root of y plus 1 minus y squared plus 2y plus 1. 1 cancel 1 minus 1. Y minus 2y is -y. So 2 square root of y, -y, minus y squared. You'll just have to integrate this one. The volume is y runs from, again, this is 0.11. So y runs from 0 to 1. 0 to 1. And this function. 2 square root of y minus minus y squared dy. And if you do this simple calculation, this will be pi root. Okay? All right. So, the example 2, 3, 4, 5 are all about Washer method. Okay? There was this specific type of application of the general method of finding volume. That is, when you know cross-sectional function perpendicular to certain axis, normal x-axis, y-axis. If you know cross-sectional area, you just integrate cross-sectional area function, right? So let's do another example. Example 6. This time, this one is differentiate. Consider a solid with a circular base with radius r parallel cross sections perpendicular to the base, perpendicular to the base are squares. Find the volume of the solid. Okay. So I'm going to draw a x-axis like this and y-axis like that. It's a circle. You have a circular region. Your base is circle. It looks like ellipse, but I just drew this y so a little bit closer to y. So this is a circle. It's a projected view from some angle. It's a circle. Radius r. Okay? And there's a lump of solid. But this solid has parallel, cross-sectional, perpendicular to the base, is a square. So I want decide to put x-axis to the perpendicular direction to these cross-sections, right? So when you cut it this way, you have to raise a square, right? The square with this one as a base length. Over here, if you cut it this way, you have a smaller square, right? Here, larger square on top of this base. And again, smaller square. Because cross-sectional, they say that these cross-sectional regions are all squares. So this one has to be, you have to erect a square from this, right? Over here, also smaller. So that's the shape. Probably the shape will be something like so some of these, your cell inside circle will go like this. I don't know. It's so hard to draw. Something like this, okay? Over there. Going down like that. So, you see? Cross section. It's a square. So what I need is, for given x, I need to find the space length. Alright? Now this is circle equation on this circle, radius r, right? And this is this point is xy. So your base will be this, y coordinate difference for given x, right? So I'm going to draw it here. So if you cut it this way, you'll have a direct square here. This point is y equals square root of r squared minus x squared. You solve this equation for y squared equals r squared minus x squared. Upper semicircle, this is lower semicircle. Okay? So this one will be x square root of r squared minus x squared. Or, you don't have to do this. Let's say xy1, xy2. Let's say xy. And this is y. Right? Forget about this. This is just x squared plus y squared equals r squared. This is the same as y coordinate. Now, base length of the cross-sectional cube is 2 times y, right? 2 times this y coordinate. So area as a function of this x is b squared, 2y squared, so 4y squared. But this xy is satisfying this equation. Your y squared equals r squared minus x squared. So this is your cross-sectional area. Okay? So the volume is x runs from minus r to r. 4 times r squared minus x squared dx. Again, this is even function. So you can just multiply by 2, take out 4 from 0 to r. Okay? Then you're going to get 8 times r squared x from 0 to r minus 1/3 of x cubed 0 to r. 8 times r squared times r cubed minus 1/3 r cubed 2/3 r cubed. So 16 over 3 r cubed. Okay? Now, example 7 is actually simpler. It's easier than this. So I'm going to just leave it as reading assignment. Example 7. Example 7, which is same as example 7 on your textbook, page 444 again. 444. So this time, instead of square, your cross-sectional shape will be a triangle. Okay? So I want you to go through this. Okay? In that case, your cross-sectional area is not b squared, but square root of 3 over 4 b squared. Because the area of an equilateral triangle will be square root of 3 over 4 b squared. You can go through the textbook. This is reading assignment. Okay? Now, example 8. Find the volume of a cone, a general cone, not just circular cone, any cone, with a base area B and height H. So something like this. Let's say this kind of cone. Okay? Okay? This area B. How are you going to find the area? Base area B, height H. So what we are going to do is place this one into the xy plane like this. Okay? This is H because you put the vertex of the cone at the origin, then your base plane will cut through the x-axis at H because this has to be height H, right? Then this shape is whatever the shape, the base here is B. So in order to find the volume of this, we have to find this area of this cross section. Now, if this is cone area, this cone, this shape will be X. This is X, right? Similar figures, because cone is all obtained by, from the vertex going to this outline curve of the base, a raise. So if you cut it parallel to this will be similar figure. When you have a similar figure and length ratio is X to H, then your area ratio will be square of the length ratio. Remember? If length is 1 to 2, the area will be 1 square to 2 square. Alright? So that means, therefore, your AX is just X squared over H squared times B. Or B over H squared times X squared. It's a quadratic function. Okay? So, your volume is from 0 to H, A of X dx, which is B over H squared out, X squared dx, B over H squared, 1/3, X to the third, 0H, H cubed, right? The B over H squared, 1/3 H cubed, 1/3 B times H. 1/3 times base here times H. So if you have a circular cone, your base area is circle area, pi r squared. Therefore, volume will be 1/3 pi r squared H. That's precisely the volume formula of a circular cone. Okay? All right. So you can use this one actually to do, for example, homework number 31 on page 447. Okay? You can use this. As long as you know base area, you can just use this. Or you can just find the A of X. Okay? Using this similarity. Okay? All right. That's the end of section 6.2. And I'll see you next time.